Good morning, everyone, and welcome to this webinar from KDI. As you see, the title is Simulating the Full CCS Value Chain with KSpice and LedaFlow. Those are our in-house tools. I will be trying to focus today on the modeling and simulation aspect of the CCS value chain, try to give you a few tips and tricks that I have learned through the years of working with this. As you can see, my name is Sigve Karolius. I'm a senior process engineer at Kongsberg Digital. I've been working with CCS now for about 3 years. Have experience with a wide variety of simulation tools and especially how to actually use simulations to gain insight into the operations and also provide more detail during your planning and construction phase of a project. So today we'll focus on that aspect of the CCS value chain, and I'm sure there will be more specific examples coming in further webinars down the line. So to start off with a little introduction. At KDI, we talk about dynamic simulations. That's our main focus. Of course, steady state is an important aspect of design, but I want to try to emphasize to you that the dynamics is too, all the way from feasibility and concept selection through to startup and operation. The dynamic behavior of your process is extremely important to bear in mind. And you can actually get started really early on. And in so doing, you can gain insight into the boundaries between the process or your process systems. This is something you're going to hear me focus on rather a lot. Experts in one particular system, say that is the amine loop, might not have considered the capacity of your compressor system when they've been thinking in terms of startup and shutdown. Of course, to a certain extent they have, but to what different situations you may end up with, that could be a wide variety of situations. So starting out early with simulations is always a good idea. Of course, in these early phases, the cost of actually making a change is small. And that's why we try to sort of use this illustration of, the simulator is in a way a magnifying glass that can help you see into the future about how and discover how your process is going to cooperate with the adjacent system boundaries. So that brings me to another pet peeve of mine, which is evolution of model fidelity. We can start out with a model that is rather approximative. And this is something that you will, of course, see throughout your project. In the early phase, you don't have a lot of data. And as you progress, as you get more data from vendors and you do more design calculations, you can make your model more detailed. And this is where it's so important to have a simulation tool that actually facilitates this way of thinking. You can't just rebuild a model every time you get new data. You actually need to be able to fill in new parameters. So it kind of needs to be ready out of the box to support this mindset. In an approximative model, you can get started by having a few intended operating conditions. You can have steady state simulations available, and you start by constructing what I typically call a skeleton of a model that you know is going to get more meat on the bones eventually, but it's a good place to start. At least you've gotten going. Once you've gotten to a stage of a project where you have a few design calculations, maybe you've even received some estimates from vendors, you fill in this data, and now you can actually start to gain some realistic transient behaviors. And of course, if you started out early with an approximative model, getting to this stage is filling in data sheets. So you're on the front foot, and that's what we're talking about here, always being on the front foot. So when you need the simulation, when you need simulation results, the simulator is ready for you. It's there and it's ready for you to use. Of course, when you get to later stages of a project, maybe you have even built the plant, then you can put in all of the vendor data sheets. Maybe you even want isometrics, piping isometrics in the model. And of course, at the end of the day, nothing beats real plant data. I mean, that is the gold standard. That is where we are really tested. And a model, the transient model, really should be with you throughout this phase of a project. It should be able to support everything. And in KDI, we typically think of this as the life cycle simulator. It's being used in several places. And the way we look at this is with our simulation tools, the process model called KSpice is typically where we start our customers in the systems engineering domain, where they can play around, they can look into how is my control philosophy, how is that going to work, will my heat integration, is it balanced, or do I need more cooling capacity, for instance. And of course, the flow assurance domain, industry leading tool, LedaFlow really is, where you can get very, very high fidelity multi-phase physics or fluid flow. So you can study flow lines and wells. Also coming up now very soon, as you probably saw in the webinar on LedaFlow, near wellbore injection simulator will also be coupled with LedaFlow, so you can actually gain insight all the way from the process engineering, excuse me, and control world down into the reservoir. An incredible tools. As you can see, I've highlighted that this is an engineering simulator. It's typically what we call it. So in this world, it's typically usable for engineers. You can do it to run all of your parametric studies and look at and study your system. But this engineering simulator can also be coupled with a control system to make an operator training simulator. We call it an operator training simulator. Of course, it can also be used for DCS checkout. So here you link together the process model and the DCS system so that the simulator really is just stimulated by the control system. You can check out all of your logic and check out signals before you start doing commissioning of the real plant. So you have an excellent idea that the major things, you always find something, right? But that the major things that you can do something about have been discovered and ironed out. So anything that pops up after this, it gives you peace of mind. That's what it does. So to start off with, I just want to emphasize to you that the idea here is dynamic simulations. They're useful throughout the project lifetime. Modern simulator tools supports this way of thinking and have been doing so for a number of years. Now we get into the meat of the presentation today, which is simulating the CCS value chain. That's what you're here to listen to, and I want to sort of want you to think of the CCS value chain in three parts. So on land here, we have our emitter, whatever that may be, cement plant, gas turbine, ammonia plant, whatever it is. This is where we want to capture your CO2 from. And then you need a capture and conditioning facility. So this is, I mean, in my experience, an amine loop. Of course, membrane technology is also quickly coming online. I will be using amine as an example in the chat today, simply because that's what I've been working with the most. Compression. Of course, once you've captured the CO2, you need to compress it and liquefy it for transportation. And when we get to the ocean part here, sorry, before I should actually mention that, for the transportation, you might be looking at transportation from two perspectives. Some of you are going to be working with a CCS hub, typical to Northern Lights, well known for that, where you get batch shipments of CO2 shipped in by ship. In other scenarios, you're going to have networks of emitters coupled together in a flow, producing CO2 directly into a flow line, and that's a completely different beast. So the simulation system needs to be able to support all of these categories. And of course, at the end of the day, we get to the reservoir and to inject the CO2. So this is really the oil and gas business in a nutshell. This is what we have been doing for a very long time. And our simulation tools, with some modifications, of course, can be readily applied to these problems. Because at the end of the day, when we model the value chain, we start on the left-hand side. We need solvent chemistry, unit operations. Maybe you need to do grade simulations to make sure you have enough power, voltage, and frequency for your pumps. That's on the process engineering side. We move over to transport, thermodynamics. We need to study bubbly flow, physical metering, slug capturing. These are all things that we are familiar with, but in the CCS domain, there is a very rapid development for the tools to be at the cutting edge of this business as well. Of course, when we get to the storage, you have dry ice formation, hydrate formation, and for instance, questions such as water ingress into a reservoir. So these are the constituent parts of this simulation. But going forward in this talk, I'm going to be trying to focus more on the bird's eye view. So what does this value chain, what is it really comprised of? Well, of course, on the capture side, there is some sort of emission process. There is a capture process, and then we have the treatment, compression, and liquefaction. Now, all of these processes, you might be an expert in one, you might need information from the other. I'm going to try to emphasize here how we can actually think of the process model as it can be made more or less approximative in certain areas, such that you can gain the insight that you need. And that's the important part here, to utilize these modeling tools to your advantage. When we get to the transport part, of course, you have batch transports in ships and flow lines, or continuous transport in flow lines. And for the storage, reservoir injection and wellbore simulations is something that's essential to look into to make sure that we have optimal energy use in our injection plant. So starting at the beginning, thinking of the battery limit and the model versatility for the emission process. At the simplest stage, we can think of the emission process as simply boundary conditions that are time varying. Now, that can allow you to do predefined transient cases, such as startup and shutdown. Typical situation for this would be if you're dealing with a gas turbine where you don't have the data to actually go into the detailed modeling of the turbine. Then we will simply set up time varying boundary conditions, and you can still look into the capture process and how the capture process will respond to the turn up and turn down curves that you have been provided by the vendor. If you go into a bit more of a, shall we say, simplified process model, that will allow you to run more complicated transient scenarios. Let's say you now have a burner and a few boilers to represent your gas turbine. Well, now you can be able to look at, okay, well, will my pressure conditions be inside of some of these boilers? How long will it take me to evaporate water once I've started the flue gas or started the turbine? And you can now look into more complicated scenarios, for instance, trip scenarios, very useful for HAZOP. You don't need to go into the full detailed modeling, but by expanding the battery limit into the emission process, you can gain more insight into how it will cooperate with the capture process itself. And of course, the full glory detailed. If you model the entire emission process, you can now look at temperature distributions in your emission plant and have the full transient capability to run a wide range of simulations. And this is, of course, also the most complicated model to build. Although it should be said, in many cases, the emission process already exists. But this is the case in Norway with the cement factory. That process has been running along for many years. So you actually have process data. So in those cases, you can actually use the process data to to build this model to help you get started quickly. And this is something that can be looked into as a huge advantage for in certain CCS projects where the plant is already well known and well understood. You can actually model the emission process. Again, it will be a simplified process model, but because you have so much data, you can actually overlay that and make sure that your dynamic is represented in an accurate way. Going over to the capture process, thinking about this from a similar perspective, you can have what I call oversimplified process, where you simply extract the CO2 from the flue gas with some sort of efficiency and a time delay. Of course, the CO2 has to move through the amine loop to get to, for instance, the compressor or all the way to the flow line. This can be interesting for someone if you're a flow assurance engineer and you need to be able to have some sort of interplay between the emission process and your flow assurance problem. Now you can actually think of, okay, the capture process, it exists. I don't need all of it, but I need something. And this is where K-Spice as a simulation tool is really excellent, that you can actually make a simplified version of the process very, very quickly with some very clear assumptions and connect your LedaFlow model at the end, and you're good to go. You probably used LedaFlow already to do your standalone flow assurance problems, and all of a sudden now you have a model that is integrated, albeit with assumptions, but at least you're started. The next you can do is to think of this as a partial capture model. You know, what if I'm not yet interested in the entire capture plant? I want to start at one end of it, typically the desorption column or regeneration column, many names. But maybe you're interested in studying, okay, how does this column behave when the steam or energy varies? You know, how will my compressor my compression package, how will that have to respond to variations in load in the column? So then we can actually look into that part of the system and leave out other aspects, because you can always add it later. That's what I typically say. You know, complexity is easy to add. It's difficult to take away. It's easy to add. And of course, the complete capture process. This is something that particularly in scenarios where you need successive startups and shutdown, now you need everything. Yeah, you even need accurate volumes for piping, etc., because the amine loading might vary throughout your plant. And in order to get a accurate transient, then you're in a situation where you actually need the entire amine loop to be modeled and simulated. And this is something that is, of course, if you started out modeling parts of the process, you now plug on or you now can plug in the rest of it. And this is how we try to evolve the models over time, depending on customer needs, of course. When you get to the compression, the treatment and liquefaction aspect of the process, this is, of course, a lot of units, first of all. So going in and modeling it in great detail right away, as you can see, what I've tried to summarize here, it's a lot of data. You might need compressor curves for each impeller. You need a detailed design of your cooling system, probably regeneration, isotherms, all the rest of it. I mean, you're process engineers, probably most of you, so you know exactly what I'm talking about. But in these cases, even if you do a simplified approach, you can gain insight into your system. Let's say you start by assuming one compression train with a fixed compression ratio across each impeller. You can get an approximative compression system built relatively quickly. You can assume, okay, let's say we have almost unlimited cooling, and also, but more importantly, assume volumes in the system, right? Because now you can say, you can actually say, for instance, these you can get blowdown scenarios with relatively accurate volumes, at least. Of course, it's not the full detailed model, but it gets you going. And again, you can get data early in the process. So even when it comes to these more complicated parts of the plant, you can start out with a simplified model and make it more detailed as you go along. When you get to transport and storage, here the situation immediately becomes a bit more complicated, because particularly for flow lines and wells, you can have a simplified version in K-Spice, where you use our built-in flow line blocks, but you don't have any multi-phase phenomena at all, really. You'll get some gas formation, but you don't get any slug features or anything like that. So here it really becomes very quickly a question of, do you want a pure K-Spice model, or do you need the multi-phase aspect of it? In our experience, it's a good idea to start out with multi-phase from early on, because then the capability is there. Of course, it's a specialized, LedaFlow is a specialized simulation tool, and it is better for these simulations than what a process systems engineering tool is from the beginning. It's also important to consider this intermediate storage question, because when you have tanks, CO2 tanks standing around, and they're supposed to be loading and offloading ship tanks, you're going to get return gas. And this is a question that is very much up for debate. How does impurities transmit between emission sites? Is it possible to actually do the offloading operation without sending any return gas to your emission site? And this is either very important to your customers, or it's important to you, because at the end of the day, you're going to get I would say, for the CCS hub, because they're going to get these impurities into their system. So also, when it comes to the transport and storage, you have to bear in mind this fidelity question. Draw your battery limit appropriately, and construct your model with very clear assumptions in mind. When we get into simulating the value chain, pulling back a little bit and going back to our original overview here, we think about this again as capture, transport, and storage. Typically, the simulation scenarios, they happen at the interface between the emitter and the capture process, between the capture and treatment, but it's also between the capture site and the transport system, whatever that system is, between of course, the flow line and the reservoir. So the simulation scenarios are absolutely, they're not limited to just within the capture site. It's also between the domains. When it comes to the capture site, we have typical questions surrounding managing heat sources and steam availability. For instance, if your emission process is highly integrated into the capture system, you might use a lot of heat from the emission process. Then how quickly can you get started? That's one question. And also, if you need to trip the CCS plant, what happens to the emission or the emitter, right? So that's the second bullet, the impact on the emission process due to any unforeseen event in the capture process. Startup and shutdown strategies. This is something that we often look into as sort of the gold standard of dynamic simulations, typically why one want to do them in the first place. In this scenario, you might also want to look into emissions management. Proof of concept. Yes, we can actually capture X% of CO2 during startup, or provide guidance for how the compression system can be designed or operated in order to minimize emissions during startup and shutdown. And of course, dispatchable operations, it's inherently transient, so it's sort of an obvious example to bring in this simulation case summary. Moving over to transport, already mentioned it before, transferring impurities between emission sites, most irrelevant when we're talking about boats. This is a scenario that I foresee is going to be, there's going to be a lot of questions. Not all emitter sites are going to have the capability of removing certain inert components or impurities. So they're going to be, you might even end up in cases where they might reject a boat because it stops off in a plant that has an impurity that they don't think they can get rid of. So this is going to be extremely important to look into. That goes, of course, into the actual process of loading and offloading a ship. Very few operators these days have an experience actually carrying out these operations with CO2. Of course, with oil, it's well known and well established. But with CO2, it's a different question. And training on this operation is going to be very valuable for them. Strategies for integrating several emitters into a pipe network. How will multiple emitters producing CO2 into a pipe network actually, how will that work in process, right? And how will maybe your capture plant react when it sees transients in a flow line? It's something that you can get started on right away before the problem arises. And certain things, such as if you want to have a feature for buying CO2 back to start your compression system, for instance, or maybe to even you want to avoid the problem of gas return from a ship. You want to be able to actually install a little boiler effectively that can produce vaporized CO2 from your liquid CO2. How this can actually be used to prove that you've accounted for this in your CO2 accounting, so that there is you can prove to the government that there will be no double counting of captured CO2. So there's a whole host of scenarios that one can look into in the transport section. For storage, initial startup of injection, low pressure reservoirs, visits from Mr. Jewell and Mr. Thompson is typically what I talk about there. Of course, it's on everyone's mind these days. A lot of interesting scenarios to look into in that regard. Successive shutdown and restart. This can be very important even for flow lines that are with aquifers, because what happens when you pressurize and depressurize several times? What happens inside that flow line? I can't give you that answer at the moment. Don't have the solution manual yet, but I'm sure we'll find out in the next few years. And of course, optimize the operation. The injection operation, we wanted to use as little energy as possible. We would love for the chokes to be 100% open and still be in complete control of the process. Is that possible? And how, if so, how do we do it? So for the storage section, there's also a bunch of simulation scenarios that's going to be very important for you to look into. So as a few final points I want to bring up: the study of transient behaviors. incredibly important to get started early, not when you need the simulation results. Then you always have to wait a bit before the model is ready, right? Reveal the potential operational challenges early on. I often say contingency in design is flexibility in operations. And conversely, if you reduce your design contingency, your operation also becomes less flexible. And that even more enhances the need for dynamic simulations. Construct a model to fit your current needs, right? And that's something that cost always comes up as a question. And it's where I say, well, let's start with what you need, and then we can build on that. Complexity can always be added. When a project sees what you can do with a powerful simulation tool, the money typically follows, in my experience, and you typically will get an expansion of the model, and also to maybe even include several partners in a project. And finally, simulation studies, they really are valuable throughout the entire CCS value chain. We've seen this already, I think we're only going to get more examples added to our list of simulation scenarios where our simulators have provided incredibly important insights early on before we've even gotten started producing a drop of CO2. And with that, I guess I'm a little bit over time, but then I'll invite you to ask questions. I have to have a look on the side here to see if there are any. I guess it's a bit early in the morning for most of you. I'll give you a few more seconds to think if there are any questions that you want to ask me. Of course, we will be doing another batch of CCS webinars at a later stage, probably looking more into specific examples, and you are very welcome to join at that time as well, of course.
Sigve, we have a couple of questions that have come in. I can just fire them at you. So, would it be possible to capture and calculate the carbon emission for a drilling rig operation?
In short, yeah. I mean, then I would say, you know, what part of the drilling operation. But again, this is something that, you know, if we have a chat, and so I understand the specific problem that you need to describe, I can either say yes, we can do this in a simplified way, or sure, the unit operations exist, so we can actually do the model the system in full.
Okay, and then the next question is, where do you recommend having the boundary between K-Spice and LedaFlow in an integrated model for capture and transport, and how do you do this?
Yeah, so we have a LEDA, we call it the LEDA interface in K-Spice. So the process simulator actually orchestrates the multiphase simulation. So it sends data back and forth, the two simulators. And I typically say, okay, how important, for instance, is your choke valve? If your choke valve is extremely important to you, you want it incorporated in LedaFlow. So that's typical for engineering simulations. We start at your final ESV valve, topside or on land, if you will, and we do multiphase all the way down to the reservoir. In operator training simulators, you typically want to include things such as mag injection, etc. And then we often will split the multiphase simulation. We will do one LedaFlow instance for the flow line, so the long flow line that goes down to a template, for instance, and we go back into K-Spice in order to capture the Christmas tree with the mag injection and all the things that you need around that before going back into LedaFlow for the wellbore and the reservoir. So that depends a little bit on the type of simulation. For engineers, I would say there is one boundary. It is when you go into the your flow system. For operator training, it's a bit more complicated because you want a wider range of simulations.
Okay, thank you for that. And the next question is, can the geomechanics of the candidate reservoirs for CO2 storage vis-a-vis designated fluid properties be modeled on K-Spice or LedaFlow to establish compatibility during project evaluation?
Oh, that's a question that goes beyond my domain knowledge. We are integrating LedaFlow with the GEM reservoir simulator. And what I would say is keep an eye out for that release, which is happening in about a month, I believe. There will be a video posted on that release to provide more information, because I'm absolutely certain that you will get many of your questions answered there. Otherwise, contact our product champion for LedaFlow, Ludivine. You'll find her contact information on our websites, and she will be able to provide you with that info.
Okay, and we'll take the last one here, Sigve. Can the churn flow model in LedaFlow be used for CCUS modeling, considering the inability of K-Spice to model slugs?
Yes, it can. It can. This is they're doing a lot of experiments these days to validate these models in LedaFlow, and the results are coming back thick and fast. It's an exciting area to be a part of at the moment, and again, the next release of LedaFlow will include many of these capabilities.
Okay, I think that's it then. We've run a little bit over time, but thank you, Sigve, for presenting this today, and thank you everyone for joining. And yeah, it's a wrap. Thank you, Sigve. Thank you, everyone. Bye-bye.